Yeah, I'll just repeat all the announcements. So, yeah, welcome to day 2. If in case you want to use the library, you can use it. I don't know if any of you know where it is. It's actually right near here. It looks like the Guggenheim. It's open from like 9 until 5:30, but you can access it out of hours just by getting a library card. It's temporarily issued at the guest house, so just ask them. The other thing is on Thursday, we're thinking of doing a dinner. So unfortunately, we can't cover it from our budget. It should be something like $20 to $30. So that's like, let's say 3K INR. If you want to come, let me know. I'm trying to figure out what the restaurant capacity is, so it's subject to that. Okay, and I think we can probably start. So yeah, great. So we have Dima's first lecture on S embeddings and maybe even T embeddings.
Yeah, thanks a lot for inviting me, for having me here, for organizing this conference. That's a wonderful place. So I'll be, yeah, the plan is actually the other way around. So today, at least, I'll be speaking about T embeddings, not S embeddings. I'm sorry. And that's going to be more Blackboard talks. However, Trishen asked me specifically to show some pictures at the start, and I agree that that's a good idea. So the plan now is kind of to have a teaser of what's going on. So that will be lectures on the planar Ising model. And by planar, I mean not only two-dimensional, but also nearest neighbor. Combinatorially, there is a planar graph on which spins sit, and that's planarity. And the bipartite dimer model. In a sense, bipartite dimer model, I believe I'm too loud. Am I too loud? No? Is it okay? Is it all right? Because yeah, I kind of hear an echo, and that's interesting. So, and bipartite dimer model, in a sense, one can think of it as a generalization of the planar Ising, though that's not true literally. However, that's kind of a more general framework, and this leads to what is called T surfaces, while the Ising model leads to what is called S surfaces. There is also another particular case of the bipartite dimer model, which is related to random walks, to something like uniform spanning trees, loop arrays, random walks. And in this case, okay, that's another specification, and we will be having a talk by Misha Basok later this week on Friday or on Thursday. Okay. Though maybe the link with dimers will not be very explicit there. So all of a sudden, you see here R22 and R21. So they are 4-dimensional and 3-dimensional Minkowski spaces. And of course, you should be very skeptical about that at the start. Why at all planar models should have anything to do with this a bit weird geometry. So a reasonable goal, actually, for this class is just for me, for giving these lectures, is just to convince you that maybe it's not delirium, that's maybe this indeed, there is something interesting there. Okay, so let us start. First, what is the Ising model? So here there is a formal definition. Let me try to be pedantic. Imagine that we have something like the square grid. Then what we do, we put spins. I believe that everybody knows this, but let me recall this. We put spins plus minus variables on vertices, and then we should define a probability measure on the set of all possible configurations. And by definition, by my definition, the probability measure is just given by a certain parameter, which will be called x, or the number of plus minuses sitting nearby. So in plain terms, each time you see plus and minus nearby, then you pay the price x. And then the more disalignments you have, and the less the probability is. So okay, I'll be more general. So I'll be working with planar graphs, something like that. My spins usually will be sitting on faces rather than on vertices, and because I'm in the planar case, there is no big difference. So here there will be sitting pluses and minuses, something like that. this guy be minus, this guy is B plus. And my parameters, so this is the homogeneous model. So this X is just, one parameter for the whole lattice. And for me, there will be different parameters assigned to different edges. So the probability of a given configuration of spins will be proportional. So Z is the partition function of the model. This is just the coefficient of proportionality by the product of all, like if this is U prime and this is U, the product over all pairs such that the spin is aligned of this variable, of this parameter. So that's just combinatorially the same. And then, of course, depending on your situation, like whatever the graph is, whatever the weights are, you may expect different behavior. And here, this is a definition that I will never be using. But what you can also say that there is an energy assigned to a configuration, and classically there is one more parameter, which is called external magnetic field, which favorizes, say, plus spins, and then the probability of a configuration is given by the Boltzmann measure. The link between the parameters is like that. So X has the same monotonicity as the temperature. So what we should understand is that this is a parameter in between 0 and 1 if our model is ferromagnetic, and it has the same monotonicity as the temperature. Later, I'll be using some parameterization. It should appear already on the next slide, actually. So why is this in model interesting? Again, I believe that it's been told by Trishen in the class or something like that. That's an archetypical example of a phase transition. So on a regular grid, like on the square grid, if you are below a certain critical value, then a typical sample that you see something like that. This is an ocean of a given color, and then there are some islands there, but they're exponentially small, and so on and so forth. If you're above the critical temperature, then what you see is a percolation-like configuration. This is an open question, big open question, to prove that indeed for any fixed X greater than criticality, you have convergence to percolation. And then exactly at criticality, you have something, some third regime, which is an interesting regime. And the parameterization of this axis that I'll be using is actually the following. So instead of working with these variables which are between 0 and 1, I'll be using something else, some variable theta e. That's just useful in some situations. And theta is a parameter which is now in between 0 and pi over 2. In particular, this pi over 8, all of a sudden, this is half of pi over 4, and there is some nice numerology. Okay, but as I already said, my primary subject for today, at least, will be the bipartite dimer model, not the Lsing model. So I do some preparations, I introduce some terminology. However, yeah, we will be speaking about something else. Still on the Lsing model, also I believe that many of you should know this by heart, but not everybody probably saw it. So why is this regime interesting when we are at the criticality? Because the model, as many other two-dimensional lattice models, okay, for other models that's prediction, and for this model this is a theorem, it demonstrates conformally invariant behavior. So what does this mean? First of all, just a small recap, what are conformal maps? Conformal maps between regions in the plane, they're just holomorphic bijections. So this is a map which is function of a complex variable, which is analytic. And then the defining property of such maps is that they preserve angles. So that's complex analysis 1. What is a bit more important is that here, this is the picture I've stolen from Wikipedia overnight, as any other, as many other pictures. So what is important is that here in Wikipedia, I believe it's meant that both guys are just planar domains. So this is a map from this square to some planar domain, which indeed preserves angles. However, the notion is more general. what you can imagine is that you have a certain two-dimensional surface in R3, for instance, and maybe in some other space, we will be going to Minkowski spaces. And as long as you are able to measure angles on this surface, you can speak about conformal maps. So there is no need for this guy to be a domain embedded. Now, what is the conformal invariance property? It means that if I show you a picture like that, drawn here, and map it under a conformal map, then you cannot distinguish the results statistically from what you would have seen if you sampled the model directly on the square grid here, not on this image of the square grid. This would be a tautology, right? It's just a matter how we represent our combinatorics. But if I start, so what's the conformal invariance? If I sample my model somewhere in a domain omega, take the limit here, and then sample my model in some other domain, omega prime, but still with the square grid parameterization. Take the limit there, and then I have a random configuration here, random configuration there, and I can try to understand what happens if I map the left one to the right domain conformally. And conformal invariance says that if I think about interfaces, then the image of this measure is just the measure there. And this is what allows eventually to classify them. So in particular, these interfaces, there must be what is known under the name SLE curves, and I will not be speaking about SLE curves, etc. And this is a famous theorem due to Smirnov, is that there is a convergence of interfaces in this setup. Another way of thinking about the conformal invariance, you may think about correlation functions. So alternatively, you can say that, so here SLE, CLE appears. Alternatively, you can say, okay, let me consider some points in my domain, in my square. Let me take their images here. And let me think about, for instance, the correlation of spins sitting at these points. So let me think about the correlation of spins in my domain omega. Okay, the omega delta. Delta means that it's discretized. And try to send delta to 0. Try to do this mesh smaller and smaller and ask what the limit is. So as it is, the limit is 0, but if you normalize it properly, and here there is a non-trivial normalization, which is 1/8 per spin, then there is a non-trivial limit, which is also a theorem. It's not by far not obvious as it is. And I'm using a kind of physics style notation. I'm saying that this is just a function of points in the domain, a certain number. And I can ask how this number is related to the similar number obtained on the right. And then the answer is that they are kind of equal to each other. Kind of, because this identity cannot hold. As I've written it, if you start thinking about the scaling, you immediately understand that something is wrong. So it's not compatible with the scaling. So here there is an additional factor, which is just the product of the derivatives of my map, absolute values to the same power 1/8. It's an exercise to convince yourself that this 1/8 should be the same. I mean, this exponent should be the same exponent as that. Otherwise, there is an intrinsic contradiction. So that's another way to think about the conformal invariance. Okay, so that's a general.
Can I ask
Sure.
one question about notation? So sometimes I see conformally covariance.
Right.
Here, what's the difference?
That's a very good point. So yeah, this is much better to say that the correlation functions are conformally covariant. So this is just what it is. However, the field theory which arises is called conformally invariant. That's just a matter of words. Yeah, that's what it is. So like this. So these correlation functions of a certain conformal field theory, and the word conformal says that it's conformally invariant theory. Whatever, but you're right. Yeah, covariance is a good word, and here is exactly the rule. What happens with these functions when I apply conformal method? And please feel free to interrupt me. Yeah, by the way, I almost didn't sleep today, so I'm completely off. So jet lag, 10 hours and a half and 30 minutes. So just ask questions.
Maybe I'll just ask, actually, does anyone have any questions so far? Anyone online have questions?
Okay.
Yeah.
There is fortunately a question on the slide. So a question on the slide is, right, this is the situation on the square grid for the homogeneous model, but what, I mean, how does these answers, how do these answers, if they exist at all, look if I start in a more general setup? I don't want to specify any concrete setup right now, but imagine that instead of the square grid, you have something. Then what? It would be probably too naive to believe that the limit here is always the same, independently of what this something is. For instance, you can think about maybe the same parameters on horizontal bonds, some other parameters on vertical bonds. So this is not fully homogeneous model, but something very, very regular. And then it's known what the criticality condition is. Actually, if you have just two parameters, then the criticality condition is that the sum of two thetas is pi over 2. And the limit will not be the same. So the limit will be just smashed, I mean, in one of the directions. So this will, it will lose even rotational invariance. Yeah. Absolutely, yeah, and that's an excellent question. Yeah, a question has been asked: what is the definition of the criticality? Yeah, on a more advanced level, you should think about maybe near critical models, and then the definition is that you have connectivity and non-trivial probabilities to see connections. Then, if you want convergence to something which is conformally invariant, then what should our language be? Our language should somehow assign to our sequence of graphs, which is behind, a certain notion of a conformal structure, a certain object that appears in the limit on which I should be able to measure angles, for instance. And that's, okay, and then still that's a question whether or not I have conformal invariance in this with respect to the structure, with respect to this. That's an excellent question. Okay, so now another character. This is a bipartite Dimer model. So what is a bipartite Dimer model? Maybe let me write the definition on the blackboard. And again, what is on the slide is just a very concrete example when the underlying grid is the regular honeycomb grid, like that, this small guy. So what is the bipartite Dimer model? I have a certain graph, and again, I don't ask much about this graph, at least at this moment. This is just something, planar bipartite. Maybe I don't even know how to draw it in the plane correctly. So because like the Ising model here itself is fully combinatorial. So I haven't insisted that those are straight guys. I mean, it's just a combinatorial object. So there is this bipartite graph. Now, to every edge, there is a parameter assigned. And my name of this parameter will be nu. So B is the Runyon notation for black vertices, and W is the Runyon notation for white vertices. So there are parameters assigned. Then Dimer configuration is just a choice of what is known as perfect matching in combinatoric. matrix, sorry. So this is a subset of edges such that every vertex is covered exactly once. And the probability to see a dimer configuration. So this D is the dimer cover of my graph. And the probability to see a concrete configuration is again proportional to a certain constant by the product of these edges, weights of these edges. Okay, so those are positive parameters about which I do not want to say anything, just some numbers. And of course, you can start playing with homogeneous setups, just trying to understand what's going on. So if you're on the honeycomb grid, so what is the advantage of this picture? Is that it's actually simpler to draw a dual picture. I hope that it is self-explanatory. So instead of a chosen edge, I draw a losange tile. Okay? And on this, it's clearly a three-dimensional object, which, by the way, has nothing to do with T surfaces and S surfaces. I mean, don't be confused. So you can see this random configuration as a, say, well, okay, it's random two-dimensional surface. In particular, at every point, there is a random height of a point. And that's, to a certain extent, can serve as a replacement of this spin variable. So we can speak about correlations of heights. Okay. And then there is a result in this concrete setup, when you approximate a triangle exactly in this way, that the height fluctuations, they converge to the Gaussian free field. Fortunately for me, the Gaussian free field already appeared in Pierre's lecture yesterday. So what is that? But it was a discrete guy. So what is that? So this is a random distribution, a random function, better to say random generalized function. So this is a function of a point z inside. It's centered. Each linear functional is also Gaussian, and the covariance is given by the inverse of the Laplace operator. When I write it like that, I'm cheating a bit because this guy is infinite on the diagonal. So in dimension 2, this, okay, in any dimension actually, when we're in the continuum, so that's an infinite guy. So how should I mitigate this question? Well, let me maybe write it also on the blackboard. So that's not a big deal. So just Gaussian free field. Well, I cannot speak formally, I cannot speak about single values, but what I can do, I can modify with something. So that's just a scalar product with a certain modifier, which is a smooth function in my domain. And then these objects, they make sense. So I can just write it as the integral over omega times omega of g z1, z2, phi z1, phi z2 over the area. This will be my notation for the area of the area in each of the variables. So I pretend that I could have integrated this as it is. Well, I cannot, however, what I can say that I have a collection of variables indexed by modifiers. And then that's still a Gaussian infinite dimensional vector, and that's what makes it properly defined. The green function is also conformally invariant. And it seems at this point, so this guy is conformally invariant. And benefiting from this question about what is conformal invariance and what is conformal covariance, this is invariant. When I map my domains, nothing changes. The green function stays exactly as it is. There are no factors of that kind. So this is a conformally invariant object. And the first impression is that we're exactly in the same situation, that there should be always, well, something nice. However, there are two setups on the hexagonal grid, and actually there are infinitely many. So there is another standard example. I believe that you saw it. So if you start with a slightly different domain, which is a hexagon, and the key difference is that the boundary is discretized in a very different way, then samples all of a sudden look very differently. So in particular, there is what is known under the name frozen regions, where you do not see any fluctuation at all, any fluctuations at all. So the structure of fluctuations here cannot be described. I mean, it would be nonsense if literally the same description applies, right? Because the green function in the hexagon is still non-zero everywhere. However, I do not see any fluctuations in some parts of the hexagon. And in this setup, there is a theorem which says that, and this is actually much more interesting because there is something non-trivial happening, is that the height fluctuations, they still converge to the Gaussian free field. However, okay, the first adjective is Gaussian, so there is a Gaussian limit. However, the covariance of this field is not the green function defined in the hexagon. This is a green function in some different complex structure. If you are afraid of these words, just think about, some different way of measuring angles here, which maybe completely degenerates near these corners. Like you imagine that just, from the metric perspective, somehow all the corners, they collapse to points. And inside of the liquid region, there is some other non-trivial way of measuring angles. If we are in such a situation, which may be a big shot, however it works, then you could speak about the green function defined in the other conformal structure. How? Because you always have uniformizations here. If you have any way of measuring angles, you can always say that there is a conformal map onto the unit disk, and there is a well-defined green function. So what's important in this slide? There is actually a zoo of possible limits. So all of a sudden, bipartite dimer model is much more diverse. So you can see very different things. And then you can ask a question, but how can I learn this conformal structure? And that's what I want to speak about. Now, two more examples on the square grid. So you may think that, okay, maybe that's something specific to the hexagon, to the honeycomb grid. And the answer is no. On the square grid, which may be nicer or maybe not nicer, there is, of course, very, very, very similar stuff. The first example is to make a link with random walks. So there is a very special class, so we already kind of understand that the boundary is very important. That boundary effects, they are by far not negligible. They change behavior inside drastically, so that's something extremely important. So there is a very special boundary combinatorics, which is again on the square grid. I hope that this is self-explanatory. So let me try to explain, nevertheless, try to comment on what is here. So I do have a square grid. This is a bipartite graph. And actually here, what I did, I split black nodes into two classes, just black and gray. So that's again a bipartite stuff. And then on the left, I insist that all corners of my domain, they are black, which is one of the two types of this bipartite class. Well, if I just did it everywhere, then I would be in trouble because this domain would have one more black vertex rather than, as compared to white ones, and it wouldn't allow any dimer cover. So I remove one of those. Okay, this is a definition of a temporal domain on the square grid. So what do we see in the right-hand side? In the right-hand side, Well, that's a bijective correspondence. I will not be proving this. But again, I believe that it's kind of, it's drawn how this should work. So this is a bijective correspondence of all dimer covers of this temporal length domain and what is called spanning trees of the graph whose vertices are black nodes. And here there is an algorithm. So each time you have a black node, you should draw an edge in the direction of the corresponding dimer. Is there any question about this bijection? Okay, so far so good. And in particular, what I'm saying that.
Can you just say the bijection again?
So the bijection is that if I have this dimer cover and I want to construct a tree on black nodes, then I take this one, for instance, I see a dimer and I just draw an edge in the direction of this dimer. Or I see this guy, I see a dimer and I draw vertical edge. And I do this for all black nodes. A claim is that provided that, as follows, provided that the boundary combinatorics is as explained, what we see on the right is a spanning tree. And vice versa. If you start with any spanning tree, there is exactly one dimer configuration on the left. So uniform spanning tree is a well-known model. And gray vertices, there is just a unique way to fill these straits, these passages between the branches, which is a part of the statement. So the statement obviously requires, it needs a proof, but I will not be given a proof. So this class is not about that. Just take this as an exercise. Now, because of this link, you might have known that uniform spanning trees, this is a model which is, speaking spanning tree, uniformly at random, is a model which has a lot to do with random walks. In particular, a branch of this tree is what is called loop erased random walk. So this thing, you should expect that it has a lot with conformal invariance, because random walks on Z2, they converge to the Brownian motion. Brownian motion is conformally invariant, so there should be conformal invariance here. Okay, what about the height function? So before, on my previous slides, it was kind of intuitively clear how to define the height function. This description of dimer configurations through functions was just immediate from the picture. So when I'm on the square grid, maybe I should do something for this, in this respect. So a statement is that one can always define the height function. This is an important definition. Here, I hope that I would have place to put it on the board. Maybe put it here. So the definition works on any planar graph. So what should I do? I have a random cover, which is blue dimers, and I choose a deterministic green dimer cover, which actually not necessarily covers my domain. It can just go outside, as in the figure. And then I superimpose the two. What I get is some edges that happen to be in both blue and green, and some loops. One can give an orientation to loops. How? Just say that, okay, let us orient blue dimers from black to white. This provides an orientation of every loop. And then one can view these oriented loops as level lines of a certain function. Each time when you go, when you cross this loop, you change the value of your function by 1, depending on what is the orientation of this line. And this defines me a function on the dual graph, which, if you give a thought for that, it generalizes the definition on the honeycomb graph. Okay, so the algorithm is that if I have a dimer and I want to define the increment of my function from, say, this vertex to that vertex, then H V prime minus HV is just the indicator that my dimer is in D minus the indicator that my dimer is in D dot. And this is just deterministic. D is just my random configuration. And denote in the figure, this is the green one, which is taken to be deterministic. And then there is a couple of remarks. The first is that what happens if I change my reference configuration, my green cover? Then it's just a deterministic shift. So if I'm interested in fluctuations, for instance, then nothing changes. So the mean changes, but the fluctuations do not. And then another remark is that in principle, you can take both random. You can take both random and independent. This is what's called double dimer model. And then, okay, it's a bit more symmetric version of it. So there is a theorem due to Rick Kenyon and this is one of the very first results on the conformal invariance, and that's a very influential result because it led to many couplings of GFF and SLE curves. Okay, many. In this concrete case, coupling of GFF with SLE2, which was then generalized to imaginary geometry. To composite symmetry. The theorem is that as the mesh size of the grid tends to 0, then the fluctuations of the dimer height functions, they converge to the GFF in this sense, just in the original structure of the domain. And another comment here in passing is that because of this bijection, you can think about the same function differently. You can ask yourself, what this function, can I describe this function in terms of the UST model? And the answer is affirmative. You can give an intrinsic definition in terms of the UST model, and this will be what is known as the winding field. So if you are at a certain point, you track the branch that goes to the root and compute the winding number of this branch. And just combinatorially, this is the same quantities if you normalize properly. So there is a certain factor which includes pi and which I do not remember. So this is an example on the side that we do have, like if we compare with the previous one, this is like the left example. And then there is an example which mimics what happened on the right. So here, these graphs are known under the name Aztec diamonds. So what is that? Here is the combinatorics. This is a subset of the square grid with this combinatorics. And you ask yourself how a random dimer cover of this graph looks. This is similar to what I've already, to the figure that I've already shown for the hexagon, the rough frozen regions. And if you never, please, by the way, raise your hand if you never saw this figure before. Okay, yeah. Let me then explain why it's natural that there are frozen regions. So imagine that we sit here and we should make a choice how this white vertex is covered. There are two choices. One is horizontal and the other is vertical. If we make horizontal choice, then we can continue in several ways. So we do not force ourselves to make any future choice. I mean, right now. However, if we choose a vertical one, then it becomes very restrictive. Because once this guy is chosen, then that guy must be chosen, and so on and so forth. So choosing a vertical one on the top freezes the whole boundary. And because of that, this choice restricts the number of remaining possibilities drastically. So this choice is exponentially improbable, which means that, okay, with huge probability, this vertex is covered by the horizontal dimer. And you can try, to iterate this argument and convince yourself that at least some small region near the corner must be frozen with huge probability. Okay, so this is something very different from the previous picture. And again, there is a question here that's a theorem which right now here I didn't give any support for this theorem, but it is known that the limit is Gaussian. But still, if you define height functions, then the limit is Gaussian. However, this covariance is not the green function in the square. This is some other green function. And you can ask yourself, is there any way to see this new complex structure geometrically? Yeah. Yeah, that's an excellent question. You can extract it from there. So if you are familiar with this limit shape business, then given the limit shape, you can find this complex structure explicitly. And this applies to any periodic grid. That's an excellent question. However, that's not what I want to discuss. Why? For those who know the Daimer model, in particular, because the story of limit shapes is actually very limited to regular grids. So in this business started by Kenyan co-authors, Kenyan Prob in 90s, it's very important that your graph is periodic. And I'm interested in something more flexible in particular. So not necessarily periodic weights, maybe very distant applications to random setups, something like that. So, and I ask myself, is there any way to observe this new complex structure just by redrawing my graph? So what is my idea? I think that maybe that's simply by drawing. Because the Daimer model, it has nothing to do how I embed this graph into the plane. I could have drawn it in a completely different way. And maybe there is a way to redraw, a clever way to redraw this graph so that for new pictures, I see just my familiar green function. This is my hope. Unfortunately, it doesn't work exactly like that, but that's a good try. That's a good try to understand to where we are going. So that's the idea. So we are still, we have a freedom to draw this graph as we wish, because combinatorially nothing changes and definition of the height function doesn't change either. And maybe I just want to find better drawing. And that's the last slide, and I still have, I believe, 5 minutes because I started 5 minutes later. So let me try to explain what is on this slide. And then we will start something more pedantic and simpler after the break. So I pretend that this is a better drawing. And at the moment, nothing tells you why. So what my goal is just to explain what the correspondence is. So first, this is clearly a dual picture. So what I'm drawing a dual, I'm embedding a dual graph into the plane. So black nodes, they become black tiles, and similarly for white nodes. Then you can notice that something something slightly less trivial happens near the boundary. So I pretend that actually combinatorially, I can think about my Daimer model on Aztecs as a Daimer model on a graph where all these white nodes are declared to be 1. So this is what corresponds to this big white node, and it has now 4 black neighbors, this, and that. So why? Because more or less of something very similar that I explained with frozen regions. So we know that among these 1, 2, 3, 4, 5 white nodes, 4 are used to pair with 4 black ones. So only 1 remains. And it's clear that this 1 can be whatever it wishes. So there is exactly 1 white node here that is connected to one of the blacks. And this is what allows me just to declare them to be single macro node and work with the Daimer model on the new graph. So what I'm saying that here there are 2 steps. First, I just combinatorially replace what I had by the new graph in which there are 4 boundary vertices, 2 white and 2 black. And then I draw a dual picture in a secret, using a secret algorithm, which I didn't tell you. Okay, so this is a new drawing. And now the tricky part. My hope was that already these drawings, when I increase the number of vertices, they provide me the right complex structure that I now should compute G in this domain, well, which is somehow maps all nodes to some new positions, roughly. And this will be the right answer. This would be wonderful. Unfortunately, this is not the case. So unfortunately, you should think about these drawings as surfaces in a four-dimensional space. So there is a second coordinate here. And before explaining how you obtain this coordinate, let me just say that, okay, we obtain some surfaces in R22. It so happens that in the limit in this particular example, so not in general, one of the coordinates collapses, and what we have is just a three-dimensional picture. And then there is a map in the limit which takes this region and sends it onto my surface. All frozen parts collapsed to points. Inside, something highly non-trivial happens. Okay, that's some map. And then there is a magic answer. A magic answer is that the right covariance structure is just given by the green function defined in the complex structure of this surface. And when I say the complex structure of the surface, I mean that now there is a way to measure angles here. This way comes from the metric of R21, which is something else, but still allows me to measure angles. And that's it. So that's a geometric description that provides us an answer to that. And the goal of the class is to understand what I'm speaking about on this slide. Question?
I have a question. So you say maximal surface, but it's maximal for what? It's like a...
Yeah, that's a maximal surface. So I wanted to save a minute for an exercise to be done during the break. However, let me first comment on this maximal surface. We know that in the Euclidean space, there are minimal surfaces. Those are soap forms. They minimize the area. So you fix the boundary and they minimize the area. In this signature, unfortunately, they maximize the area rather than minimize. So just think about this, that they are minimal surfaces and you will be right. Well, that's just, that's the very same variational problem. Okay? And now an exercise to be made during the break. Take, I don't know, sacrifice a sheet of paper. Do the following procedure. Just fold it so that there is a vertex. Okay? Try to make it degree 6 rather than degree 4. Then unfold. Lemma. The sum of two black angles equals pi. Okay? Is it clear, the question? So I pretend that any folding like that, independently of what the degree is, gives me a vertex such that the sum of black angles is pi and the sum of white the same. And moreover, what I also pretend is that this is if and only if. If I draw such rays, then there is a way to fold the paper as it is done. And that's a good point for the break.
Huh? So, any questions in the audience? Or... yeah.
Hello.
Now it's better.
Could you explain what is the second drawing on the one which is red and blue, but before being on the surface? Yes, this one. Yeah.
Oh, that's just an illustration of how the map works. This is nothing. That's just coordinates in this original guy. Okay. So what I tried, what we Sanjay tried to visualize here is how the map works. Like this part, this red guy is mapped into this prolongated region.
I see. Okay, so,
So
it's just illustration.
Just an illustration here.
Okay.
There is nothing specific about these darts, whatever darts.
Thank you.
Shape, yeah, coloring.
Any other questions? Maybe I just have one. So now
The word one.
There's one there? No, it's okay. You go.
Hello. So for the Ising spin correlations, they have a limit, it's conformally covariant, and the scaling exponent is 1/8. So my question is, how does it generalize to monomer insertions for the dimer model? Like, does it?
You ask what is the scaling exponent, or?
Yeah, is it still supposed to always be 1/8? Or?
No. The scaling exponent is 1/2. Yeah, monomer decays like 1/the distance, I believe. It does not generalize directly.
Okay.
There is a link between the bipartite dimer model and the Ising model, which is called combinatorial Bosonization. The key article is Julien Dubida from 2012. So there is a link between monomer correlations and products of those guys. So there is some structure behind, but that's not a short question and neither a short answer. I apologize there. So spin is not directly a monomer. That's something else. Though there is a link between the two.
I just have one naive question because I'm confused about R22. So you can have surfaces which, I mean, the notion of a maximal surface is confusing me because you have two negative things in your metric,
yes.
right?
Well, maybe let us postpone it. I don't know. So yeah, I'm happy with this.
Discuss it later.
Yeah. That's a very good question. So what always happens is that this is a space-like surface. Indeed, there are two negative directions, but the surface is always, it has gradients smaller than 1. This what allows you to define a fair Riemann metric here, positive definite Riemann metric, and what allows to define angles. That's long story in short.
Okay,
that's
great.
An excellent question.
Okay, great, thanks. So shall we start at 20 past? So 10-minute break. Is that okay? Everyone? Okay, cool. So 10-minute break and then we go again. Thanks.